wondered what chemicals go into your shampoo and body wash that you use every morning in the shower? Or the hand soap you use after taking your morning deuce? Looking at the ingredients list can leave you with more questions than what you started with. Today we'll take the first step in helping you better understand these ingredients by looking at a common chemical found in these products with the complex name cocamidopropyl-betaine. Cocamidopropyl-betaine, or CAPB for short, is a pale yellow liquid that can be found in everything you see here and more. But why? Well, to understand, we need to look at its molecular structure. The first group of CAPB is a cocoyl fatty acid chain made of single bonded carbons. The different forms of CAPB are solely dependent on the number of carbons in the chain, with the most common form of CAPB being lauramidopropyl-betaine, which has a chain of 12 carbons. The other groups of CAPB are an amide, propyl, and a betaine group, which is named after its discovery in the species Beta vulgaris, commonly known as sugar beets. When these groups are put together, the name cocamidopropyl-betaine starts to make a lot more sense. The most important thing to note about the overall structure is the change in polarity. The carbon chain is nonpolar and hydrophobic, while the betaine group is polar and hydrophilic. This type of molecule with a hydrophobic tail and a hydrophilic head is known as a surfactant. When using soaps or shampoos that contain CAPB, the nonpolar molecules are represented by the clusters of dirt on our skin and the oil in our hair, while the polar molecules are represented simply by the water which is found in the aqueous soap solution. When both come into contact, the CAPB molecules embed their hydrophobic tails into the dirt and oil to avoid the water, while the hydrophilic heads stay in the water. This causes the dirt and oil to separate from the body, allowing more CAP molecules to cover it and form what is known as a micelle. The formation of micelles creates a mixture of water and oil in the form of a foam or stable emulsion which has a lower surface tension than an unstable emulsion, hence the name surfactant. This mixture can easily be washed off the body by rinsing with water, effectively leaving you squeaky clean. In the industrial scale, CAPB is synthesized by reacting dimethylaminopropylamine, or DMAPA, with a fatty acid coconut oil, which is usually lauric acid, which as mentioned earlier, has a carbon chain of 12 atoms. This reaction forms dimethylaminopropyl cocoamide, as the primary amine is more reactive than the tertiary amine. Caustic soda is then mixed with chloroacetic acid and water for 1 to 2 hours at a pH between 4 and 5. The temperature is then increased to between 85 and 95 degrees Celsius, and the reaction is continued for an additional 3 to 4 hours. When components are clear, sodium benzoate and glycerol are added to the solution and reacted for 1 to 2 hours before the solution is cooled to 50 degrees Celsius, where the pale yellow CAPB liquid is ready to be packed up. While coconut oil is extracted from coconuts, you may be wondering how DMAPA was made in the first place by CAPB manufacturers. Well, it wasn't. It was bought. Okay, fine, we'll show you how it's made anyways. So, DMAPA used in the industrial process can be made by two processes, where the first is a mycoreaction using dimethylamine and acrylonitrile as reactants. The first step of a mycoreaction is an acid-base reaction in which hydroxide functions as the base and removes the acidic hydrogen, in this case the hydrogen on the nitrogen, giving a dimethylamino group. In the second step, the nucleophilic group, the dimethylamino, attacks at the electrophilic alkene carbon in a nucleophilic addition reaction, pushing the electron to its conjugate carbon, making a carbon anion. The last step involves the deprotonation of a water molecule, giving dimethylaminopropylnitrile. After this mycoreaction, dimethylaminopropylnitrile simply undergoes a hydrogenation reaction to produce DMAPA. But what about acrylonitrile and dimethylamine? Are they produced synthetically? Yes they are, and each of them have their own unique synthesis. Acrylonitrile is acquired from the catalytic amoxidation of propylene in what is known as the SOHIO process, which is named after the company Standard Oil of Ohio, which discovered the process. The SOHIO process involves the reaction of propylene with oxygen and ammonia over a bismuth molybdate catalyst to produce acrylonitrile. Dimethylamine, on the other hand, is obtained from combining methanol and ammonia at a temperature between 250 and 700 degrees Celsius using a zoolite catalyst. From a marketing standpoint, the CAPB market has maintained a relatively optimistic growth globally of 3.96% over the past 4 years. In 2013, $461 million worth of CAPB was sold on a global scale, with this number increasing to $518 million in 2016. Experts believe that the market for CAPB will continue to grow in the next few years, and that by 2021, the global annual revenue will reach $575 million. As a chemical commonly found in personal care and cosmetic products, it is typically disposed of along with wastewater. Remember being used in your shower, your sink after your morning deuce? Well, as you may have guessed, it ends up in lakes, rivers, and oceans, which is home to aquatic plants and wildlife, all of which contribute to the ecosystem in some way. Aquatic ecosystem health and function are crucial as they are part of human recreational, economical, and cultural systems. Surfactants such as CAPB are also used for minimizing the effects of toxic algae blooms as they prevent their growth and movement underwater. Any environmental effects that compounds such as these might have must be accounted for to ensure that no harm is caused to the organisms living in those areas. In fact, tests performed on Ulva lactuca, a common form of green seaweed, showed that there was noticeable damage caused to the cell membrane. The tests were performed at typical concentrations of surfactant for algae bloom treatments. Because CAPB is readily degradable, only its acute effects are considered when testing for environmental impacts. The APVMA performed experiments studying its effects on animals and found that the toxicity towards aquatic invertebrates was minimal and of no real concern. Patch tests performed on humans indicated that impurities such as amidoamine are the substances responsible for the irritation and allergic reactions caused by contact with CAPB. These molecules remain in the final material as impurities during synthesis. Contact allergy tests showed that patients were synthesized the DMAPA impurity rather than CAPB. Higher concentrations of CAPB did not increase irritation, while increased levels of impurity did have an observable impact. Despite these factors, CAPB is still widely used today and regarded as safe in standard doses by the Cosmetic Ingredient Review Panel and the FDA. With that being said, we hope this video helped you learn everything there is to know about CAPB and help just a little bit more with that never-ending quest to understand those daunting ingredient lists on your morning routine cleaning products.